In this video, we'll take a look at where we're headed in Chapter 1. That's the fundamental theorem of arithmetic. And then where we will start, and that is the well-ordering axiom. First, let's have a look at the fundamental theorem of arithmetic as it's stated in the textbook and the statement that we'll eventually be proving. So we have for every integer n except 0, 1, and -1, every other integer is a product of primes. And furthermore, this prime factorization is unique. All right, so that's kind of the key part here that we're going to try and show. So if we have two prime factorizations of the integer n, let's say p1 through pr and some q1 through qs, then to show uniqueness, we need to show that these two factorizations are the same. In particular, the r is equal to the s, meaning there's the same number of factors. And then if you reorder, let's say, the q's, then you can get it that P1 and Q1 are the same up to plus or minus. So P1 is either equal to Q1 or it's equal to negative Q1. And then P2 corresponds with Q2 that way, and PR corresponds with QR. So basically what we're saying is prime factorization over the integers is unique up to the order of the factors and the sign of the factors. So you could have a plus or minus. Because, for example, of course we know we get the same number if we change the order of multiplying, but also imagine Q1 had a negative and Q2 had a negative. When you multiply those together, the negatives just cancel out, right? So it's kind of unique up to those two things. All right, so that's what we'll eventually be trying to prove. Now, we could just, day one, try to write out a proof of that. But what are some of the things that we would need to know? Well, first we have to work with primes, right? So we need to have a definition. So, what is a prime number? And one thing that complicates that just a little bit is we're not just looking at positive numbers here. We're looking at kind of over all of the integers. And so that includes, -1, -2, -3, and so forth. So it's over the integers, not just positive, positive numbers. So that's just one little, complication we'll have to take care of. But once we start talking about primes and looking at some kind of factorization like this, well, of course, we have to know a little bit about factors, right? So what does it mean for one number to be the factor of another number? And another word for factor that you're probably familiar with is divisor, right? They mean the same thing. But so we need to know something about what a factor is. And then, of course, that leads into knowing some things about multiplication. I'll just maybe abbreviate here, multiplication and division. Right, we're starting to get into some of those properties of multiplication and division that lead to a definition of factors. And then, of course, we need to notice that over the integers, some operations kind of work better than others. So one note here is any two integers, things like 0, 1, 2, 3, 4, and so on, and then also -1, -2, -3, and so on. But any two integers can be, and I'll just abbreviate here. I'll just put a plus for added. They can be subtracted from each other, like 3 minus 2, things like that. They can be multiplied and still get an integer, but not always divided, right? So division isn't as well defined in the integers as the other three operations. And again, I'll just put some abbreviations here, but not always divided. For example, if we take 3 and we divide by 2, right, that is not an integer, right? We have to introduce, fractions and rational numbers, things like that. But if we're just working over the integers, something like this is not defined in the integers. All right, so we have to be a little careful about how we work with division. Okay, so what we're going to do through Chapter 1 is really kind of the reverse of this process in some ways. We're going to talk a little bit about these basic operations and make sure we kind of understand what we can and can't do in the integers, and make sure that we can use these operations the way we need to. Then we will talk about division a little bit more, factors, divisors, that kind of thing. That'll lead to talking about primes. And once we have all of our definitions and all of our little results put together, we can give a nice proof of the fundamental theorem of arithmetic. Okay, so this is kind of what we need to do. So let me just kind of sketch that. So this is what we need. Okay, now where will we start? And the point here is we could keep going down this rabbit hole, right? So what's kind of the thing one level down that you need to know before you can talk about the next thing? But you don't want to go forever, right? At some point, we just have to stop and say, like, here's our starting point, and then here's what we're going to do with it. And for us, our starting point is this right here, two things. We want to start with the fact that we have the integers. So we have our collection of numbers that we're interested in, and we use the symbol, this kind of a math blackboard bold or math bold Z here. So we have the integers and the operations addition, subtraction, multiplication, and division, keeping in mind that division of two integers is not always possible. All right, so just our basic facts about the integers and those operations. And then the other thing is we're going to talk about something called the well-ordering axiom. So this is our starting point, which we already kind of know our basic properties. We'll review those a little bit as needed. And then we want to introduce this idea of the well-ordering axiom. The idea of this is it's something that everyone's going to believe is true. And then using these two things, we're going to work our way up through this list and then provide a proof of the fundamental theorem of arithmetic. The well-ordering axiom is the following statement. Every non-empty subset of the set of non-negative integers contains a smallest element. And think of this as a statement about the set of non-negative integers. The set of non-negative integers. It's a property of this set that if you take any non-empty subset, it has to have a smallest element. So let's look at a couple of examples there. So first, the non-negative integers themselves. So the non-negative integers, of course, it's a subset of itself. We're going to use the symbol in here, and it's the elements 0, 1, 2, 3, and so forth. These guys can also be called the natural numbers. So also called the natural numbers. Just making a few notes here about them. Some places you look will not include 0 in the natural numbers and others will. This textbook does, and so we'll do that. So non-negative integers and natural numbers are the same thing in this book and through this course. Now, so those guys, that set has a smallest element, right? Has 0. Now, what the well-ordering axiom is saying is if I take a subset of the non-negative integers, so for example, I could take just, say, the even non-negative integers like this. Well, that is a non-empty subset of the non-negative integers, so it should have a smallest element. And of course it does, it has 0, right? I could take something like the positive primes. I could take 2 and 3, 5, 7, 11, and so forth. And again, that is a non-empty subset of the non-negative integers, so it has a smallest element, in this case 2. All right, so that's the well-ordering axiom. Now, what would happen if we tried to replace the non-negative integers with a different set? So let's just kind of play around for a second. What if we cross that out and said, well, what if it was all of the integers? Well, in that case, it fails, right? Because you could take the set of integers themselves, which is this set here, like this, and you can see that there is no smallest integer, right? You can always, if you give me, say, -10, I can say -11. If you say -1,000,000, I'll say -1,000,001, right? There's always an integer smaller than whatever integer you give me. Looks like I misspelled here. Integers. Okay, well, whatever. Misspelled that word. Anyway, the point is it fails for the integers. So that doesn't work. What if we said, okay, so can't do that. What if we did something like non-negative rational numbers? And tried to do that. So then we're looking at, the set. It's hard to kind of write that set out, but of course we're looking at things like, a half, and you can do a third. Of course, you have all your integer values in there too. I'm just listing a few elements, but you get the idea, right? It's all those positive fractions that we can get. And of course, 0 is in there as well because we're looking at non-negative rational numbers. Now, the idea here is the set of non-negative rational numbers does have a smallest element, 0, but not every non-empty subset has a smallest element. In particular, we could pick the positive rational numbers. So if we look at that subset, the positive rational numbers has no smallest element. All right, and so as an example here, if you give me some positive rational number r, then I'll say, well, that's bigger than r divided by 2, right? I can divide by 2 and still get a positive rational number if r is a positive rational number. And then if you think maybe r over 2 is the smallest, then I'll divide that by 2, and I'll get r over 4, right? Okay, so that's the idea. So it turns out that the non-negative integers are kind of a special set in the sense that every non-empty subset contains the smallest element. And that's not true for the integers or something like the non-negative rational numbers. All right, so that is the well-ordering axiom, and that will be, seems obvious enough that we can assume it's true, and that'll be a building block for us as we go through this chapter.